So I'm very pleased this week to introduce David Hertzog. So he's one of our colleagues from our more or less neighboring institution in Seattle, down there in Washington State. Obviously not allowed to visit us right now, but he's giving a remote talk. We're very pleased that David is able to do this because, as many of you know, there's a big new result in the press in the last 10 days or so. It's been all over the news. That's what he's going to talk about today. David is, as I said, is a professor at the University of Washington. He's also he's director of the Center for Experimental Nuclear Physics and Astrophysics, and as well as being a member of this G-2 experiment collaboration, he's also known for his teaching, where he's won awards and completely revamped undergraduate teaching and so on. So he seems like the ideal person to get to talk to us. So it's all yours, David.
Hey, thanks a lot. Thanks for inviting me. And let me just get started right away and tell you about what we're up to here. So first things first, no surprises. We determined the G factor of the muon to be this large number of digits here. It's 12 digits, the number that's in your credit card if you like memorizing your credit card. And the last two digits here represent the uncertainty on the G factor. And I'll come back to say what this is in a minute. And that's a pretty small uncertainty. But the experiment isn't known for saying that we measured the G factor. Typically, what we talk about is this little piece here below the couple of zeros. So if you lop off this part, this is what we call this is G-2, just G-2. But we don't talk about G-2. We talk about G-2 divided by 2, which is the muon anomaly. So you'll hear me say words today like the muon anomaly. I might say you'll see a mu time to time, most of the time. Sometimes you might see G-2 written like that, but it always means this piece of the G factor, which comes from some physics I'm going to mention in a moment. And this is the result that we had from the first measurement from 3 years ago now of the experiment you saw on the cover there that I'll describe in a little bit of detail. So the relevant scale for this first measurement is always going to be, in everything I say today, in the units of part per billion. The total uncertainty on run one for us was 460 part per billion. And you'll see as I go along some things that are numbers that are typically smaller than that or in comparison to that to put the relevant scale of the study. So just doubling back for a moment again, here's again a mu defined as G-2 over 2. And so what is the G? So the G is that G factor is that proportionality in spin 1/2 particle right here between its magnetic moment and its spin. And this is the charge over the mass times 2 ratio. And so about 100 years ago-ish, Dirac realized that the G factor should be exactly equal to 2.00000 for a point like no dimension spin 1/2 fermion. So you could say, okay, what's a spin 1/2 particle? Well, you could take a proton or a neutron and immediately see that they have large anomalous magnetic moments. And so why would they have large anomalous magnetic moments? Well, that's because there's another part to the expression which allows for an anomalous piece. There's the point-like Dirac piece and an anomalous piece, and the anomalous piece can come from internal structure. So if you have a hadron like a proton, which has internal quarks running around, they're making currents in a way, they have their own magnetic moments of the quarks, and so you get an anomalous piece from the substructure. But then there are particles that don't have substructure, like the electron doesn't have a substructure, or the muon doesn't have a substructure at the level that we know it, or the tau lepton doesn't have a substructure. These are point-like particles, so we're back to step one. So how do they have an anomalous magnetic moment? Well, they pick one up from interacting with the vacuum, with virtual fields, and as they live their life in the vacuum, they have quantum fluctuations, which picks up a little piece. And you'll see this in a minute and explain a little bit better than that in a moment. So the G-2, what we call the G-2 test, is to compare a precise calculation of the G factor, or the G anomalous magnetic moment, to test the completeness of the standard models, to test the measurement against the prediction. And both, it turns out, can be done to about the exact same level of precision. So how well does the standard model predict the quantity right now? Let's first go back quite some time to around 1947. We're still talking about g is equal to 2 here, and we begin to see deviations of the g factor from 2 at about 0.1% level, which are observed for this for the electron. And this led to the development, along with the Lamb shift, of the development of quantum electrodynamics. And here we see the typical Feynman diagram, and you're going to see some similar looking things in the next couple of projections. Here's a muon, and it's living in a magnetic field. So it's kind of connecting in here with this magnetic field lightly. And now, as it lives its life, it's suddenly emitting a virtual photon. So it goes in and out of this possibilities of virtual photons and other things we'll see. And that's the quantum fluctuation at the lowest level of quantum electrodynamics. So if you've taken a second year, probably graduate field theory course, you may have had to walk your way all the way through the calculation of this particular diagram. And this diagram has a very nice and sweet answer. It's just the fine structure constant alpha divided by 2 pi. If you do that, the number here in the denominator is like 858. And so that's what this first piece is. In fact, that's the dominant piece. And it was very important for Schwinger, so much so that he put it on his gravestone. So, well, he probably didn't put it on his gravestone, but somebody did. So this calculation, QED, is the most precise theory we have in physics. And over decades, it has reached extraordinary levels of precision. Complicated and more complicated diagrams. You can always draw more of these things and other kinds of trajectories and topologies. Not so many years ago, this paper was published where we are already up to basically 10th order. Diagrams as complicated as that. It's called QED 5th order, but it's all these 10 sort of connection points here. The takeaway, this is at the bottom, I'll say this a couple times, the takeaway is the uncertainty in this is absolutely negligible on the scale of anything we care about. And so the next thing you can do is say, okay, well, what about other standard model particles? So for example, because we have what's called an electroweak theory, that was quantum electrodynamics, what about a weak interaction? You can take any one of those little wiggles I showed on the previous page here, like this, and you can insert, instead of a wiggle, you can insert the neutral Z. Now this is a heavy particle, so it contributes a lot less because the muon has to emit that if you want to catch that as a way to look at it. Or you can do a complementary diagram here where there's a W and a neutrino cross. These are the first order weak diagrams, and they're pretty big effect. They're 1,300 parts per billion, so they're multiple times the uncertainty that we have. But the uncertainty on this calculation is, again, negligible. Even at second order calculations have been done and so on. So we totally know QED, and we totally know the weak interaction. So what about what else can you do? Well, the difficult problem in trying to calculate g-2 in the standard model is not those basic fundamental particles, but it's hadrons. It's the difficulty that you cannot, the idea of doing perturbative processes to calculate this doesn't work when you're doing really low energy, strong interaction particles like this. So here's again this a little virtual photon. And if we were still talking about QED, you could put a positron and an electron here, and you would call this vacuum polarization diagram. So it would be a photon to E plus E minus to the photon. But you can as well, with the correct quantum numbers, put a pi plus and a pi minus here, for example, or other things that connect to a photon that has a 1 minus quantum number. And so this is called hadronic vacuum polarization. And we'll see how well they do that in a moment. Now, if you go up a more complicated step forward, the next diagram, and this one is very nasty because you can't get this one, as you'll see, from data in the past. In the past, this was always done from data. In the past, this was always done from QCD models that people came up with, which are not complete. But here's one that has 4 connections to the outside world from the muon. And this is an exchange of pseudoscalars, a pi 0 or an eta or eta prime, like that. And this is hard to get to. So in the theory up until not so many years ago, this diagram was always blamed for why the old experiment may have looked different than the standard model theory. But what's been recently done, and here I have my colleague's picture, Martin Hofdirektor, but he worked with all of these people, Colangio and others, over the last 5-6 years. They developed a data-driven approach to this, a dispersive calculation, which was just a staggering recipe and a calculation that actually was able to use data from experiments and nail this diagram down to a solid prediction. So it's 154 part per billion, and it's going to be going down, but this becomes no longer the disease that may have caused g-2 to look like a signal of new physics before. But what about this one here? So this one, the data-driven results on this one, I should say at the bottom, in both cases, lattice QCD is coming along very strongly. They're contributing already to this diagram, and there's papers, all kinds of lattice calculations of this one, which are beginning to enter the game. So in hadronic vacuum polarization, let me just walk you through how this works, because this entirely comes from data from E plus E minus collisions. So you take the diagram like that, and you bring a pair of scissors along. Let me get this out of the way. I think there's something in the way of your screen here. And I cut the diagram with the scissors like that. Boop. And so what I've got is this little piece on the left, the little virtual photon, and the pi plus, pi minus. And you say, well, how am I going to generate that with something I know? Well, I can put the generation of that with a vertex that's fundamental in E plus E minus collision. So this is just basically data that people take in all kinds of accelerators and all kinds of experiments across the world. There's Chloe, there's Barbar, there's Bell, there's SND, there's CMD2. There's lots of things that go into the compilation of absolute cross sections of hadrons to muons. And this is just a recipe that's absolutely well known and not at all controversial down here. The hadronic vacuum polarization is just some kinematics, an integral from kinematics and all of these cross sections. So that's what delivers that number. So the takeaway on this one, though, is the uncertainty right now is driven by this. It's 340 part per billion. So this is still the largest uncertainty in the standard model. So some years ago, the theorists around the world who were doing things in different ways got together, and they themselves formed a rather large collaboration and have met a number of times. And the last time was in Seattle, where we organized the last workshop. And the result of that workshop was a nearly 200-page physics report, which is published, which is a full compilation. And there were little discussions and arguments, and we brought all the groups together to try to agree on a conservative prediction, meaning not an aggressive error bar, but a conservative prediction of published material that gave the best and most reliable standard model prediction. And the idea of this was every time there's going to be a g-2 release of a number from us, these folks would precede us by giving us the benchmark. And so in our collaboration, we only will quote what comes out of this team rather than picking and choosing of individual results. A couple of years from now, they're going to update, we're going to update, and we'll check again. Okay, so this is the standard model value. Again, it looks similar with all those digits, and the uncertainty on it is about 35 or so parts per billion, as I said. Okay, 358 parts per billion. Yeah. Well, if you just take a quick snapshot and put their number here, it's not like their number moved around too much from previous standard model calculations over a while, but the confidence in this number is much, much higher. And the confidence in this number is higher because of the data-driven approach and the fact that when they had any disagreement among teams, they took a conservative and not an aggressive approach. So you can see this error bar is larger, for example, than this person's calculation. They took a larger sort of superset to make good brackets. And that left us with something like a 3+ standard deviation comparison to the old Brookhaven experiment. This data was taken exactly 20 years ago. So let's talk about what this might mean later. But for clearly, it's been a very, very long time in which there's something different between the standard model and the experiment, and there's only one experiment, so it simply has to be checked. So it's definitely time for a new measurement. And so here's a little snapshot of the team at one point, the collaboration in front of the fountain in our campus. And it's a very interesting collaboration. may have never worked with such a broad group of folks before. We come from particle physics, nuclear physics, atomic, optical physics, accelerator, and we have theorists who are in the collaboration. All of them are combined with their different communities and so on, and different tool sets that they bring to the table. But we're all there to measure g-2 to 140 part per billion eventually. And that requires something like 20 times as much data that had been taken at Brookhaven over 3 years, some 20 years ago. So we're assembling equipment and a method to do that and analyze that data. So the diversity of the physics is actually sort of reflective in the way we just published 4 papers at once. This is unprecedented according to APS, but we dropped 4 papers on the archive. They're all published. This last one up at the top just got its final proofs in yesterday because it's dragging along a little bit. But there's a PRL on the cover. There's a paper in PRD that's about the muon precession frequency. There's a paper in the PhysRev A, which is about the proton precession frequency, which is magnetic field in terms of the protons NMR. And there's a complicated paper in PhysRev, accelerators and beam, about the very complex beam dynamics corrections. I'm going to lightly touch through all of the important parts in my colloquium today. Okay, if you take a breath and you're just asking, like, how do you guys do that experiment? So this is the fundamental principle of the experiment, and this is an unchanged recipe for decades and decades now. This is an nth generation version of this experiment. You start off by realizing that if you put polarized muons into a storage ring, 2 things are going to happen. By a storage ring, I mean just a simple vertical magnetic dipole field. So just think of this as a big, big magnet. And a charged particle in a big magnet is simply going to go around in a circle, which it does. And the black vector here is the momentum vector, and it goes around with something we call the cyclotron frequency. Simple enough. It takes 150 nanoseconds to go around once. The red vector represents the spin direction of the muon. And because if g was exactly equal to 2, that red vector would line up with the black vector at all times. But the red vector goes a little bit faster around than the black vector, so that 29 times around this storage ring, the red vector has gone 1 extra time. And that difference between the red vector frequency and the black vector frequency is the cyclotron frequency to the spin precession frequency down here in the expression I've written. And that's called the anomalous precession frequency. And the beauty of that thing is we can measure this, and we can measure the magnetic field, and then we do long division to get a mu. It's simply that. We measure this frequency, and we measure this magnetic field, and do long division. So it's a little bit more complicated than that, obviously. You can't just put particles in the ring and think they're going to swim around on their own. You have to have some kind of vertical containment. And that's achieved by adding electric quadrupole fields around, which turns this thing sort of into what we call a large penning trap. So if you put in a large electric fields, then there's an additional term that can, and I'll come back and show you what this is. There's an additional term from the electric field, and there's an additional term because the muons themselves are going to be swimming up and down a little bit. And those 2 things are negligible to 0 on some conditions, but if the motion is very nearly planar, if it's planar, it's 0, but it's very nearly planar. And if the momentum is exactly equal to the kinematics right here, which we call the magic gamma of 3.094 GeV over C, then this expression out front of the B cross E electric field term goes to 0. So it's not exactly true, but it's close enough to be true that the corrections are relatively small and very well-known corrections. Let me recap a couple of points here. There's 4 miracles of nature that allow us to measure g-2 to sub-part per million precision. First, nature gives us polarized muons for free, because in pion decay, they come out for free because of the helicity conservation here in the weak decay. So they just come out. You can't get them unpolarized if you want to. The anomalous, second thing is the part I told you, when the anomalous spin precession frequency is proportional to g-2 because of this red vector minus black vector difference. The third point is that magic momentum, where you need to store the muons have to somehow be contained vertically in a magnet. At the right momentum, this electric holding field doesn't perturb the spin frequency. And then the final one, which we'll come to a little bit more, is how do you know which way the spin was as a function of time? Well, if you look at the parity violation in the weak decay, that encodes the spin direction in the energy that the detectors will see. We'll come back to that with a little animation. So A mu, the way we write it, a more professional way, the way you'll see it in the Phys-Rev letter, you'll see this expression. So A mu is obtained from two frequency measurements that we make here, and well-known fundamental factors that tie things to the right units. Because here we're measuring a muon precession rate here in a field. And in the denominator, and I'm going to explain all these funny factors here, in the denominator, we're measuring a proton precession rate. It's a co-magnetometer. And so to get this to be the muon rate, not in the proton rate, we have some connections between the proton and the electron and the muon and back and so on. But those things are known very, very well. All of these are in the box here with the citations that you can look for later. The net effect of all of these is something like 25 part per billion. So it's negligible on our scale right now. So let's start back and say, how do we get those polarized muons? They come for free, but they don't exactly come without a lot of effort from the Accelerator team. So if you look at this, this is the Fermilab Accelerator complex. It starts off with 8 GeV protons, a massive amount that come every few in cycles that aren't being used by the neutrino program. They go around that ring, and we split them into 4 bunches with a lot of radio frequency applied. Each one of the bunches then goes around, and it comes down this line one by one and strikes the target that used to be there to make antiprotons. The distance from here to this triangular shaped ring is about nearly 300 meters. And in that time period, this blue circles turn into blue, which has become a muon. And we run those around the ring here. And as we run them around 4 times for only the reason to get rid of the background, and then we insert them into our storage ring. This is a very complicated process, but it delivers a uniquely pure muon beam. The pions have all decayed away, like at the level 10 to the 5th have gone away. And protons, which are in the ring, are so slow that when we run around this blue triangle 4 times, they've gotten on the other side, like a track runner, they've gotten over here, the muons are over here, and we just knock them out of the way with a sweeping magnet. So only muons come into the ring and some background electrons. So this is the picture of the ring again, and here's where they enter. They enter through this last sequence of quadrupoles, and they've got to go inside the magnet there. And the first thing to see is, how do we know what's coming? Well, we have instrumentation along the way that measures the intensity, and then we have sort of hodoscopes that measure the profile of the beam as we sneak it through this corridor in the back of the yoke of the magnet and through this inflector magnet, which cancels out the field. And then it arrives about 77 millimeters off to the side of where you want it to be, and you have to kick it onto the orbit because it has to go back. It's going to go around in a circle, but you got to kick it once so that it lands on the green circle and stays stored. So there's a device. It's right here at 90 degrees from the entrance. It's plates like this. It gets an enormous shot of current and produces this field that looks just like what is in the black plot right here. It's like up and down, and it bounces around because of impedance mismatching there. And the particles have the intensity of the red thing. So you'd like to kick them all the same way. You don't quite get to do that. But the field of the kick is something like this. The B field goes down, that kicks them outside, and then the B field goes away. That's the fall that follows this thing. It'd be ideal if it was a square pulse and went straight, but it's impossible to build that, having it go up and down, making about 280 Gauss on and off in 140 nanoseconds. That's hard. To keep them in, I told you we needed some electric quadrupoles. And so electric quadrupole looks like this in manifestation. There are 4 regions painted orange here. There's positive plates here and negative plates here. That makes a positive going particle rejected up and rejected down, up and down like this, and pulled back and forth out like that. And so they nominally, before each time we fill the ring with muons, we charge these things up. We charge these things up. They nominally go up with a 5 microsecond time constant. This is just your standard RC time constant. And they're ready to go by the time we take data where the red dash is. This is time here. And we want to start taking data here. This is an important thing that cost us 1.5 years of our lives. 2 out of 32 high voltage resistors, I'll show you a picture later, were bad, and we'll come back to that. And they had a time constant which was very slow. It created a dynamic effect for the stored muons for the first run. This is, of course, immediately replaced once they were found at the end of the run. But this data set has this problem. So here you go. Take a ride. You're a bunch of muons, and you're inside the vacuum chamber, and you're zooming around one time around the ring. You've seen quadrupole plates. You're going to see some straw detectors right there. You're going to see more plates every once in a while. You're going to see some open regions now and then. If you're a muon now and you're in that ring and you decay, your positron will have lower momentum, and so it's going to curl to the inside. So this is a good picture right here. If I decayed here and I stuck a detector over here somewhere, the positron will curl to the inside and hit that detector. And that's what we pick up on for our precession signal. Now, life is complicated. So because the beam comes in with a natural dispersion and a natural divergence vertically and horizontally, it's going to actually swim back and forth. This blob is real data. This is the tomography of real muons as measured using the straw tracker chamber, which back projects the picture in a couple of places. And it has a nice, beautiful frequencies. This is the frequency of the mean moving back and forth, and this is the frequency of the width, as you see it there. And we expected that. That's always been the case. But we do have to embed that into our fitting equations. The problem was, in the end of the day, we want the average position of that. And it looks something like this avocado plot. And you'll notice that the avocado here is not centered here. This was one of the problems. So the next thing that we have in the ring is all the way around the inside of the ring are electromagnetic calorimeters. And those calorimeters, here's a picture of one. Here's one of my students assembling some of the last cabling on it. He built all of these. It took pretty much a day to build every one of these. And the other thing that's all the way around the ring and unseen here are 378 pulsed NMR probes that are above and below that vacuum chamber that was in the movie that we saw. And they're spaced in little groups all the way around the ring so that we can use those to monitor the magnetic field at all times. So the fourth point of that, the 4 miracles, was the fact that the energy spectrum of the positrons which come out of the muon decay encode the g-2 frequency. So again, here's the ring. If I blow up this picture, you'll see one of our detector stations here. This is the business end of the detector, which is in the magnet. It's pushed into the magnetic field. The positron curls in, hits that thing. It's really made out of these 54 lead fluoride Trinkoff crystals with this beautiful SIPM readouts. All of this was built at UW, by the way. And when a positron hits that, you get a very sharp timing signal and you get a good measure of its energy. Digitized here at 800 megasamples per second and 12-bit, we get a very, very good measurement. And this is about only 8 nanoseconds wide, just to give you an idea. It's extremely fast detectors. So then, because this is what happens that the detectors see, this is the direction of the muon's momentum in red and the direction of its spin as the thing precesses around the momentum vector in blue. And what you see here is some of you might remember the word the Michel spectrum, but boosted to this laboratory frame. This is the energy spectrum that the detectors see. And you can see that the high energy is breathing back and forth, exactly in tune with the alignment of those vectors, or the anti-alignment for the minimum. So if you start collecting the data for all events above the green line, you get something like this. And this is only a matter of minutes. This is real data. So this is 3 minutes worth of data, and you start building up this wiggly spectrum. This is officially called the wiggle spectrum in our collaboration from some reason, historical reasons. And basically, it's this kind of spectrum that you fit to get that frequency. It's encoding this precession rate. Okay, now the precession rate was on the numerator. The denominator was about the magnetic field itself. So the first thing, of course, is you have to bring the magnet. We brought the magnet in 2013 to Fermilab from Brookhaven. We reassembled it. It was tricky to do. And then they had to turn it into a uniform magnet. So on the side of that magnet, you see a C shape like this. There's lots of parts to it, but the business end of it is just 9 centimeters in diameter all the way around the ring in azimuth. And these 9 centimeters, ideally you want to be the most vertical, pure magnetic field you can possibly make. To achieve that, there's lots of things that Gordon Danby developed when he designed this back at Brookhaven decades ago, which was the adjustments of all of the pieces of the yokes, the poles, the wedges, top hats, shims, and the surface coils. And the way you measure that with these probes that are all over the place is you always see a so-called free induction decay signal. So you're taking protons typically in petroleum jelly or water, but we use petroleum jelly. You pulse them over, they spin around in the magnetic field, and then they wind themselves back up at the free induction decay. And a really good free induction decay has a lot of oscillations and a very, very slow return. For a probe that's of the order of millimeters in dimensions, it can look very good if there's no gradient. But if there's a gradient across those few millimeters, you pick it up like this and you see something funky here like this. So the way that we adjusted all of these things over an entire year's time is essentially by building a trolley that had 25 of these probes and pulling it around before the vacuum chamber got. You take a look at this thing. This is this is real data. So basically, imagine you're moving around the ring in azimuth. That's where the red dot is right here. And at each place, you're constantly measuring the field, and then you're developing from that a multiple decomposition of it, which you can then feed back to a computer program to make the next adjustments. So what we did with that wasn't bad. We got after all of the things that we did, the field looked exactly as lumpy as it did at Brookhaven when Brookhaven was done. This is the dipole field in part per million. The blue one is Brookhaven, and the red one is us. And okay, we got to the same point. We wanted it better. So then an idea came along that was developed called, what if you put 8,000 tiny lamination strips in there at the top and the bottom of the vacuum chamber all the way around. You build these pieces to exactly cancel out the places where the mu is locally different. And so you build sort of an inverse template and glue them on there. And with that, I want you to watch what happens to the red line here. This is from 0 to 360 degrees. And this is the uniformity of the field and the lumpiness here. So as they're installing these plates and testing it, the whole idea got suddenly instantly better. And in the end of the day, we ended up with a magnetic field about 3 times more uniform than they had. Okay, so now let me get to the analysis quickly. First of all, we did have some challenges. The temperature in the hull was very bad the first 2 years, and that meant we had to follow the magnetic field because the magnet would go open and close. It's tricky. We had some, the kicker could not reach its high voltage, it would spark. So the beam ended up here instead of here. And we had these 2 bad resistors, which meant that the optical lattice around the ring in 2 places was funky. And it meant that certain frequencies were changing and the average storage position was changing. Okay, now the data. Like any precision experiment, you have to do multiple things to get it right. Multiple analysis teams, as many as 11 different efforts to measure the precession frequency, lots of calibrations, lots of blind analysis techniques were employed. Many specialized systematic tests were made without the beam or different uses of the beam, and a document database with something like 25,000 documents since we started. So it's just extraordinary amount of stuff. I had this planning thing on my wall board for a long time, and basically this is the analysis flow from left to right of all the pieces that had to eventually end up with a mu. And you see this little funny creature here. We called it, for whatever reason, an elephant in the room. It was the thing we didn't want to talk about. It was a problem that we saw. And eventually there was a second elephant in the room, another problem that cost us 1.5 years. The other way we more professionally put that whiteboard together was to write this master expression. So A mu is just really all of these factors. It is the measured precession frequency that you get, corrected by some small corrections that we can add linearly for the electric field, the swimming of the pitch, and 2 things that I'll tell you about later. And then divided by the magnetic field, which is the calibration of the field, where they are and some corrections themselves. So these things look like the following things. There's a blinded clock frequency, the measured precession frequency, the electric field correction, the pitch correction, a muon loss correction, a phase acceptance correction, an absolute calibration of the field in units of Gauss if you want, a field tracking multiple distribution, a muon weighted distribution, a transient from eddy currents, and a transient from the quads that charge. And so we have the numerator up here and the denominator here. So we start with an easy one. This was beautifully done, organization of a blinded clock. We never do these things where we know what's going on other than the clock is ticking at a frequency that's very close to 1 second, but it's not a second. And so that was set up by people outside of our collaboration. They basically tuned the clock with a blinding, wrote it down in envelopes. So I have some envelopes right here. And we couldn't open those until we're completely done. There's no uncertainty in this clock, though. It's incredibly stable. Now let's go up to the detectors. When the detectors made those pictures you saw, the pulses, we have to keep their gain to a few parts in 10 to the 4th over the time period in which the rate is changing. So this is where the Optics Institute of Pisa came in. They built this incredible laser system in a big hut. Every single detector is sitting in front of a pulse laser with many monitors for the stability of that laser. So we know that the gains are correct on a short-term, mid-term, and long-term cycle. The other thing we have to do is make those detectors super fast to reduce the idea of pileup. And pileup happens when something like, here's a high energy muon. This is something electron, we'd like this. Suppose it's just the right one. But now here's two low energy electrons that add up to the same energy as the red one, but wouldn't have been in our plot because they would have been below the threshold. If they come and we don't recognize that, they come with a different spin phase because the muon spin here and the muon spin here is different just by the traveling from here to here. And that's a big problem. So the energy spectrum, log scale, 0 to 3 GeV here is all you would normally get. You would normally get the out here and straight down like blue. But with pileup, they actually look like that. And so we have to correct this whole mess here. And we have many methods to do that. Even with fast detectors, we have to make that correction. So here's that little wiggle frequency. And normally any person would just fit that with a simple function. Anybody, I always say any professor could fit this one. There are 5 parameters: the intensity, the lifetime, the amplitude of the asymmetry, the frequency, and a phase constant. The phase constant represents what was the spin at t equals 0. Now, if you do that, you get this horrible spectrum here of a residual of the FFT of the residuals, meaning there's a lot of other frequencies, and also the chi-squared is like 2 instead of 1. It's a bad fit, and you end up with this stuff. But that stuff is, I already told you where that's going to come from. The beam is sloshing back and forth, and the detector sort of looks closer to it, farther, closer, farther. So that gets embedded on top of this wiggle frequency. You can't see it here, but the fit knows it's there. And the other thing is sometimes muons leave the ring. So instead of following a nice straight exponential decay, they come at their own rate of leaving the ring for other effects, which we won't discuss much. And once you fold both of these factors in, then you can get a good fit. And the good fit basically now is a perfect chi-squared, and the residuals are, the FFT of the residuals is just dead 0, nothing. So that's easy. We know how to do that. We've been doing that for a long time. And then you have to do consistency checks. The fit doesn't depend on when you started the fit. The fit doesn't depend on which calorimeter you used. The fit doesn't depend on what energies you used. And the fit doesn't depend on any of the analysis techniques that we use, multiple techniques and multiple groups. There are multiple team names here, technique names here. It's really statistics limited at 434 parts per billion, and the systematics is very small. So now the denominator, I promised I'd come back and decode this omega p prime tilde t of r symbol for you. It's really all of this red stuff. The prime here indicates that we use the shield, we reference to the shielded proton NMR frequency. So for specialists, they'll know what that particular thing means. And that we do at a reference temperature of 34.7 degrees C, which is the thesis of Bill Phillips that still stands to this day to measure that absolutely. The tilde above this, decorated sometimes here, simply represents that we're going to not be interested just in what the magnetic field was, but the field that the muons themselves felt. So you have to fold the two together. You have to fold the field with the muon distribution, and that's the tilde part of this business. So the steps to obtain this red stuff include the absolute field calibration, and there we use multiple probes, very complicated process, a completely separate magnet system at Argonne National Lab to calibrate one probe against the next, then to take the standard candle and calibrate all of the probes in our ring to the standard candle. And that was done beautifully, and the uncertainty on that is below our budget that we had planned for that. Then periodically in the ring, we need to map the field multiples all the way around when the muons aren't in the ring. I'll show you how. And then constantly we have to monitor the field when the muons are in the ring. And then we have to measure where the muons are in the ring and put that stuff together to get the right answer. So this is the device we use. This is the second time you've heard the word trolley. This device actually goes in the vacuum. It comes out of a little garage in the vacuum. It has 17 NMR probes, which I've placed by PowerPoint precisely where they probably are, I hope. And then this thing travels around inside the ring every 3 days. And so if you imagine it going around the ring, and each place at every 5 degrees, it can make a little snapshot even faster of what the field looks like there, and then there, and then there, and then there, and then there. So imagine that going all the way around. You're getting all of these little slices of the field, which you can average or do what you need to do with. So then in between that time, the 378 fixed probes are above and below these yoke plates in these locations here, and they monitor the field so that you have basically a trolley measured perfect multiple representation of the field, say here at this day, and now maybe 60 hours later, you have another one here, and somehow in between with the magnet moving around because of temperatures and other instabilities, things have wandered all the way around between these two. But this wandering to go from here to here has been tracked moment by moment by these fixed probes. And we use basically 2 fixed points connected together. You can use the random walk technique called the Brownian bridge to lock them to get the uncertainty on that. And we do that carefully. But then the next thing you need to do is at each point, you have to now know where the muons are. So again, we have that intensity diagram folded on top of these contours, and the contours are basically these contours. And that gives us the magnetic field that the muons have seen as they go around. Okay, let's get some real quick things. This is well-known effect. This is the electric field correction. It's a very large correction. You can see 489 parts per billion. It's bigger than our uncertainty, but its own uncertainty will be small. And so if you put your eyes here, this is a quadrupole field, a positive plate here, negative plates here. And imagine you're a muon going into the page. So I have an X on you as like an arrow. And so if you do the cross product of a V cross E, you're going to get a vector up in orange here, which is what we call an emotional magnetic field. And that's what changes the spin. So if you're not at this exact momentum, then you get this effect. And so because the muons have a muon momentum distribution, which is across this thing, I'm using this exactly, I scaled it exactly, then we have lots of muons that are not exactly at that momentum. But we know there's a simple recipe to add it up. And I won't do more than that, but tell you that we know it very well. This uncertainty is going to go down. It's a little tricky thing that I can mention only later. Similarly, the pitch correction is well known. It's a pretty big correction, but you can see how well we know it. This is easily measured because we have trackers which measure the amplitude of those oscillations. And the oscillations just factor into a tiny difference. What it really means is, look, you're not going orthogonal to the field. You're going at an angle. You feel a slightly different magnetic field. Now, this is like, hold on to your intellectual moment here, and let me try this out for you. But there's 2 effects that came along, which hopefully won't show up a year and a half from now when somebody gives a talk in the future. And that is related to the average spin phase of the ensemble. So I first have to remind you that this was a simple 5-parameter fit. And phi 0, this phase constant, is just which way was the ensemble's average muon polarization when they were injected. Suppose they were injected forward on average. But what if that later in the fill, that population didn't have that same average phase? So if phase was a function of time like this, then if the Taylor expansion of that would give you a constant plus a time related term, and then you would rewrite this so that omega A plus this phi prime piece times t, again now plus a new phase constant. You wouldn't know that, but you would have an omega prime instead of an omega a here. So you would have the wrong frequency. So you have to watch for this. This is a rule of this super important rule. Do not let the phase change. How could it change? Well, muons do leave the ring, and in the first run with the bad storage conditions, they left the ring, let's just say 5-10 times larger than they do now, more often. And if there's a correlation, it requires some double correlation thinking, but if there's a correlation between phase and momentum, that's not zero, and a correlation between momentum and who leaves the ring from being a muon loss, and that turned out to be not zero, you combine them together and you get an effect. We developed an entirely data-driven version of this to figure out what it was, because if you do this just in your head, you could come up with 120 part per billion shift. But when you did it, what we actually did is we measured these factors, both of them, a complicated story that we did at Washington, and the answer is negligible, totally negligible. Now here's one that cost us 1.5 years of our lives. So the picture on the left, just let me tell you what the picture on the left is for a moment. This is a intensity diagram of where the phase, this is the phase angle of muons depending on where they decay in that circle. So this is 9 centimeters across, and if they decay up here or they decay down here, and you made a wiggle plot out of muons that only decayed here, or a wiggle plot out of muons that only decayed here, they would really differ by these purple to orange colors, like 20 milliradians. This is huge, just enormous. We're trying to keep things to 10 microradians, and this is an enormous change. So you think, well, that's a fact of life, it turns out. And that's just a fact of the acceptance of the detector. There's a decay cone for number 1s and 2, and it's just a slightly different preference for when does the wiggle plot actually maximize. So that's always going to be true in the experiment in the past, now, and so on. And it wouldn't matter as long as there's never a change in the distribution of the numbers of 1s and the numbers of 2s, because you can always add up cosines of the same precession frequency, that's the same, that have slightly different phases, and you're going to get the same, you're going to get the right result. You're going to get the same precession frequency, and you're going to get some average phase angle. Well, the fact is, with the bad resistors, the beam squeezed down. So the 1s and 2s got closer together every time we did it, like, whoa, 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 like that, just systematically through the field. The beam squeezed itself down vertically. And that caused, that's what's measured here. You see a slight change in the vertical width. And that would never happen except for the bad resistors that were embedded in one location. And then what that did, you can convert that into a change in the phase on average, and that looks like this. And then you can take that change in phase and build it back into the fit function, and you find out, yeah, indeed, there's a shift from the true value of the frequency you should have got to the one you measured of about 158 part per billion. And the uncertainty on this is relatively generous. And this is really, this was a nasty problem that took us 1.5 years. That's why we didn't publish a while ago. But fortunately, after thoroughly understanding it, and it would take 40 minutes or so to tell you all the other things behind this, it looks in control. There's now 2 magnetic transients, so it just keeps going, right? Because this is what precision physics is about. And one of them was discovered again here for the first time, and will be around a little bit, and might have been around at Brookhaven, but we estimated at Brookhaven, it was lucky that it didn't affect it. And every time you pulse these quads, they're mechanical. There's a lot of forces on them, and they started to vibrate with a natural frequency, which turned out to be darn close to how often we injected beams. So they kept building it up like a resonance. And that's what you see here is a magnetic field that's flying back and forth just inside the plates, not anywhere else. But if you look really closely at when were the muons in the ring, this is a time scale of 100 milliseconds, and the muons are only in the ring for like 600 microseconds. If you look each time where the muons were injected, they're kind of lucky and fairly small, and you add that up, and the net effect of that is that it made only a tiny 17 part per billion net change to the magnetic field compared to what we measured it to be. But we have a very, very large uncertainty on this, because at this moment we're still still mapping this everywhere around to make sure we know what it is. We built special equipment to map this, and we will this summer we'll complete that job. So this was the original elephant that we didn't know what to do with. Hoped it would go away. And the other one is pretty natural, which is just eddy currents. If you make a great big magnetic transient at the beginning when you make a kick, it produces currents in the vacuum chambers above and below, and those currents themselves are magnetic fields. So this took multiple efforts until Dave Kaywall developed a really beautiful fiber magnetometer with a Faraday magnetometer. Is basically you bring polarized light through a certain kind of a crystal that will rotate its polarization down and back, shoot it back out. The sensor rotation is able to pick up the magnetic field. We're really talking about milligauss fields on top of in the middle of a 1.4 Tesla field. It's a super hard measurement to make, and the device, of course, has to be all non-magnetic in order to even do it. So that turned out to be pretty reasonable. And never at Brookhaven, all we said at Brookhaven is we think it's less than 100 parts per billion. This time we actually measured it. Okay, so then we come to the point when all of those numbers are done. We have what else do we have? You have a big Zoom meeting, right? You have a great big Zoom meeting. And then we've gone through weeks at this point. All the documentation is published, presentations, error analyses, and so on. And then we have two envelopes. So I have an envelope here. Chris has an envelope here. We read them off. We end up with the same numbers. This is the decoded number. They get typed into this live spreadsheet, and instantly we see the result, which is here. And basically, everyone who's not muted is screaming at this point because, first of all, for many of us, we're not sure if this thing is even going to be on the screen because, you start having demons go through your head and you have no idea whether somebody made a mistake and you've typed the wrong number. But what it means is this is the old Brookhaven experiment. This is the new one. It's basically got a smaller error bar by about 20% than the entire Brookhaven with this first batch of data. You can put them together to get the new experimental average and compare it to the standard model. And now it's something like 4.2 standard deviations. And the net, interestingly enough, the net uncertainty of these two together is 350 parts per billion, which is very coincidentally the goal of the Brookhaven experiment. We got cut off by an experiment by, was it Doug Bryman? I'm trying to remember, maybe. Anyway, at one point there was a rare kaon decay experiment that got priority, and our experiment was stopped, and now we finally come back to it. So how well did we do compared to our budget? It's kind of interesting. The blue bars are the ones that matter. The orange bars are the corrections. They don't matter. The only thing that matters is the blue bars. The ultimate goal is that the net error is where this green thing is at 140. The idea is that the statistical error will be 100 and all the systematics combined will be 100. So most of these are pretty good. You can see they're pretty small. This quad one will go down. This phase acceptance one will go away completely, I think, or essentially completely. And many of these are well within budget. So in the first year already, we're in pretty good shape. So what are the consequences of this result? Well, I had multiple ways to answer this question, but I'm going to start by not telling you things about the standard model, but some bigger view consequences. For this collaboration we're in, we've only looked at this much data right now, 6% of it. We have this much on tape and we're about here, planning to get to here. There's a lot of motivation for us to finish. We've confirmed Brookhaven and now it's like onward to do the job. And also we know where we should spend a lot of our extra time on what are the largest systematics. It's always important to look at your systematic error table and start picking off the big ones. For other precision muon physics experiments, I would say the stock markets have gone up quite well from U to E, MEG. These are charged lepton flavor violation experiments. Another G-2 experiment with a different concept in Japan. They're shown here. And then the look elsewhere effect is a fun thing, but what I mean by look elsewhere is let's look at other precision physics experiments that might be sensitive to other pieces of the standard model. So, B decays, lepton flavor universality test, CKM unitarities, molar scattering, parity violating electron scattering, electric dipole moments, things like this. These are all this is showing you that if you make a really good experiment that can do precision measurements, it can pay off. And for theorists, we have no need to motivate them. In 1 week, there's already 58 citations to this paper I just showed you. It was only released last week. So let me flash very importantly that my group from UW, these are all grad students in our group over the time. These 4 have graduated. These are on the way done. Some postdocs that we've had. These guys are both professors now. This is a fairly new guy here. And some senior people. That's Alejandro Garcia and myself, Peter Camel, who've done a ton, Yar Casper, who's sort of Scotty in the engine room, Eric Swanson, who do lots of stuff for the magnetic field. They all worked on different things. So accelerator physics, magnetic field, developing all of the detectors and analysis routines. This is magnetic field. This is the guy that built all the detectors. Hannah and Bryn built the incoming detectors and done all the online stuff. Josh is doing all of the computing kind of stuff. Everybody has a different role. So I want to thank you for your attention. Stay tuned. The two takeaways are that we confirmed the Brookhaven result and that there's stronger tension now with the standard model, and that remains interesting. We could talk about what that is. I have backup slides on what physics it is and so on if you're interested in that. And I'd like to, of course, acknowledge that this work doesn't happen without 200 people from all kinds of talented institutions around the globe. This was all of us. Interestingly enough, in the spring of 2019, we all coughed up enough money to go to Elba, where we thought we would basically be able to open the box. So thank you.
Right. Thanks very much.